Hello, I am Shamli Singh, and for CS259 today, I'll be talking about using cuDNN to parallelize neural networks with GPU. The contents of this presentation will be the introduction to this topic, and then followed by convolutional neural networks. I'll talk a bit about the different layers involved in CNN, followed by schemes of parallelism in CNN. This would be followed by a graphics processing unit, and then I'll be focusing on the main point of NVIDIA's cuDNN library. I'll be verifying some of the results by experimenting with the MNIST dataset and cuDNN, and I'll be showing it to you as a form of a demo video at the end of this presentation. So, as we all know, machine learning is surrounding us every day. We have so many different applications which involve machine learning. Take, for example, it starts with our phone or our Google Assistant at home or Alexa. You just tell her to do something for you. That is the basic machine learning which all human beings are experiencing every day. And then there are recommendation systems on uh, shopping websites like Amazon. But there is some form of machine learning which is not directly impacting us. Say, for example, a few years ago, Google mentioned their project of identifying diabetic retinopathy by using image classification. And they were classifying the images of the eyes of patients in India. So, uh, the experiments like that involve image classification, which involves deep learning, a form of machine learning. It's actually a subset of machine learning. Well, this is one part of my presentation. I'll also need to highlight the Moore's law, which we have already discussed in a very, I think, in the first class of CS259. So Moore's law states that every 2 years, the number of transistors double on a chip. But there is a limitation to how small the chip can get and how many transistors can it fit, which is why the parallelism was given a big push by many researchers. And the reason we are studying this subject is because of this limitation. And of course, we do have the option of quantum computing, but it's still considered far fetched. Researchers are still looking into it, and there'll be some time before it really reaches the common people. And then we also have, I'll be pondering on GPUs as well. And as a non-gamer, I seriously have my GPU underutilized. I've paid way too much for it, and I don't think I'm utilizing it enough. And I'm pretty sure many of you who don't spend too much time on gaming are finding similar things happening to them. So now I'll talk about CNN. It's not the news network, believe me. It's convolutional neural networks, or it's also known as ConNets by some people. And it's a deep learning technique. And like I said before, deep learning is a subset of machine learning, which in fact is a subset of artificial intelligence. And it's used for image classification. And uh, while there are many different types of CNN, uh, the basic idea behind a CNN remains the same. It consists of two types of layers, convolution and pooling. And the, we call this deep learning because there is a sequence of convolution and pooling layers. So you can imagine it as a 7-layer cake. Each layer, let's say each convolution layer is the spongy part, followed by a pooling layer of the icing between two spongy layers. And the last layer is the classifier. So in terms of the cake, it's the icing that tops the cake, and which also consists of chocolates and cherries and whatnot. So yeah, you can imagine it like a layered architecture. And I'm discussing convolution layer and pooling layer in detail right now. So a convolution layer is used to identify the features, basic features in the images that we provided to it. So like lines and edges and any other small features. And for identifying these features, we use something called as a filter. Uh, so uh, because it's an image and each pixel is not dependent on the pixel next to it, we it's believed that the CNN works locally, so it preserves the spatial relationship. Like then it's a 3D tensor. So we are thinking about three dimensions here: the height, the width, and the depth of the image. So for a black and white image, the depth is considered to be 1, whereas for RGB, that is red, green, and blue, it's considered to be 3. And then there is the next layer, which is the pooling layer. So uh, in the convolution layer, a large amount of information is gathered by use of filter, but the pooling layer is responsible for condensing the output of the convolution layer to a smaller set of information. And max pooling is the usual type of pooling that is used in CNN. Also, there is also the average pooling available, but it's not that popular. So, if you want to visualize these two layers, then this diagram is in Act 1. So, I have a 28 by 28 input layer, and I have this small window of 5 by 5. So, at a time, uh, say only 5 by 5 points in this input layer are considered, and and a filter is applied at this point, and the output of the filter this this one point in the next hidden layer. Now, this is at the point 1 1 or 0 0 if we are really talking in computing terms. So the index of this point will be 0 0. Now, this window has to move towards the right and down as to find more points in the hidden layer. Now there is some concept here known as a overlapping or a non-overlapping type of hidden layer. So if this window moves by 1 point to its right or 1 point downwards, then we call it an overlapping type of window because 4 rows or 4 columns remain common. So in this particular diagram, it's a overlapping window, and for non-overlapping, the rows won't be common between each window. Then we have a pooling layer. So this is a modified diagram. So I have this digit image here, which is a 28 by 28 image, and in the previous layer which we saw, convolution. So I'm getting a 5. I'm having a 5 by 5 window here, which I'm using to get the points in a feature map, which is 24 by 24. And as you can see, there are 32 of these, which means 32 different filters have been applied. So each feature map corresponds to one filter. So this is the output of the convolution layer. Now I'm applying a pooling layer of 2 by 2, of the window size of 2 by 2. So my 24 by 24 feature map is converted into a 12 by 12 feature map. And again, there are 32 such feature maps because, well, I'm condensing the output from the previous layer. So this is the next hidden layer. And this is a view of the complete CNN. So we have already seen something till here. And for this purpose, for this MNIST data set, I'm applying another convolution and pooling layer. So I've used a slightly different strategy. I've completed this 12 by 12 into a 8 by 8 feature maps, and instead of 32, I have 64 feature maps. So I'm assuming that two filters were applied to each of the feature maps here, which turned it into a 64 layered out 64 node output. And then again I have a pooling here, which gives me a 4 by 4 feature map, 64 in number, followed by my icing, which is the classifier layer or the softmax layer in this case, which gives me the output of 6. So 6 has been identified as the digit in this handwritten image. Now we've seen CNN, but we also need to realize how parallelism can be made possible in the CNN. So there are 4 different types of parallelism schemes. First is the obvious one, data parallelism. It's also known as the mini batch approach. So the idea here is to divide the data into n separate batches and providing each batch to a separate core. So each core computes the entire neural network on its batch of data, and so it can be visualized well with this diagram. So say this is one processor core. It has some data provided to it. It works on the data, and the output of the data is independent of the output of the other processor. And because it's independent, there is no communication between the processors, which means there is no overhead. And there are various different types of layouts possible, data layouts, and the most popular one is the NCHW. So what really the data layout I'm talking about is the way the data is stored in the memory when it's first loaded in the memory. So NCHW means the elements along the lowest dimension, which is the W here, are stored first and that's stored consecutively in the memory, whereas consecutive elements along the H dimension are stored in a stride of W. Stride as in the length in which the data is stored. For the C dimension, the stride becomes H into W, and so on. And the point we can note here is that NVIDIA's cuDNN library, which we'll talk about later, is also popular for this type of layout. Then we talk about model parallelism. So we have seen before that it's a 3D tensor in convolution neural network, and model parallelism converts it into a 4D tensor. Now it's not really a difficult leap that the fourth dimension is the n, which we talked about previously. So n is again the batch size, but each core computes different step of n. So which means that, okay, so if you see this diagram, each step is computed separately and each core computes different step. So so each core is dependent on each other, and which means there needs to be some communication between them, and of course which means this scheme of parallelism is quite expensive due to the communication overhead. Then there is the pipelining. uh, we have already studied pipelining in our class, and this pipelining is no different from that. So the computations are overlapped between consecutive layers. So let's say some computation starts first on processor 1, let's say the first convolution layer. Then the entire process is passed on to a processor 2 for the pooling layer, and so on. So it's really possible to do this in steps like backpropagation. These are some detailed steps which we have not talked about before, and those are really not the details we need to get in right now. But the point to note here is that the pipelining works very much similar to what we have seen before. So, and it's helpful in reducing the processor idle time, even in terms of GPUs. And the fourth type is hybrid parallelism. It wasn't a difficult leap. So it's used to overcome the drawbacks of individual schemes of parallelism. So we have seen there is communication overhead in model parallelism, but it can be better suited for some applications. So then the best idea is to hybridize it with something else. And some researchers have already done this before with AlexNet, which I talked about earlier. So they have used data and model parallelism together. And when they used each of these separately, they found the speed up to be 2.2 times. And they had used just 4 GPUs. And with 4 GPUs again, when they combined these two schemes of parallelism, the speed up obtained was 3.2 times. And it doubled when the number of GPUs was increased to 8. So it became 6.5. And the point to be noted here is that the loss of accuracy for this model was just 1%, which is quite insignificant if we consider the whole scenario. I mean, we are getting some better performance for just a slight loss in the accuracy, which can be bearable for most applications. Now we'll talk about GPU. Most of us already know what a GPU is, but I thought it would be best to just revise the concept once. So GPU, or a graphics processing unit, was first used by Sony in its PlayStation in 1994. Uh, that was way before I was born. And even I didn't know that Sony had used this, which is a surprise. But it was revived by Nvidia in 1999 with GeForce 256 graphics card. So that's the very first graphics card which they marketed for gaming community. And the graphics card is a highly parallelized architecture with 100 times process. So the point I was trying to make is the number of processor cores on a graphics card are multiple of 100, whereas on a standard microprocessor on my laptop, I have like 4 or 8 cores, I'm not even sure, but it's not more than that. Each core is called a streaming microprocessor. So you can see here, each of these is a separate core in the graphics card, and each of them has its own L1 cache. Each of them is connected to one single L2 cache and one single dynamic RAM. And if you have looked into it quite seriously, then I think most of you might be able to understand that this is somewhat similar to what we have seen before. It's a SIMD type. We can call this as in Flynn's SIMD architecture. So if so for data parallelism, which we have seen before, if the data is divided into it's multiple data because it's divided. So some data goes to let's say first SM, and some data goes to next SM, and so on. But the instruction is same, which is applying the convolution layer. So that is the SIMD architecture. You can visualize it like that. And now we officially come to the NVIDIA's cuDNN. This is the topic which I've been dying to get to. So NVIDIA's cuDNN is a library extension to the CUDA, which was released in 2014. So CUDA stands for Compute Unified Device Architecture. I know the name doesn't really ring much of a bell, but all I can say about it is a parallel programming platform and application programming interface for graphic processing units. And it was first released in 2007. Now, what this really means is it helps softwares to use the graphics card in our machine for performing parallelism. So instead of parallelizing on just 4 or 8 cores on our microprocessor, the Intel microprocessor, it would instead use the graphics processor. And the cuDNN library specializes for deep learning computations using the CUDA platform. So basically, we are providing abstraction for GPU parallelism for programmers. So programmers and machine learning enthusiasts don't have to worry about the parallelism or how to use the GPU. All they have to do is just use the library and they're all set. And like I'd seen before, NCHW and NHWC are the data layouts which are supported by cuDNN. And if you read the paper, I've already mentioned that the NCHW layout is the most popular one because it provides better results than any other data layout. And this library is supported by some really popular frameworks like TensorFlow, PyTorch, Piano, and Caffe. All of these frameworks are used for deep learning extensively, and I'll be using one of these soon. So, for my experiment, I thought that I should be supporting my presentation with a short demo because I wanted to know if cuDNN really works. So, I decided to work on the MNIST dataset, which I talked about earlier. So the dataset was developed at NYU Current, and it consists of handwritten digits from various sources. And these researchers have compiled that data into one huge dataset, which consists of 60,000 training samples and 10,000 test samples, which is a big amount, huge size of the data, and it can be freely downloaded from this website. But if you are really trying to save some data, or if you don't want to download it on your machine, it is freely available in the Keras library. So Keras is a popular library used for deep learning applications, and it works well with frameworks like TensorFlow, and I'll be using it too. So, and in fact, I used the dataset from Keras itself. For my experiment, I used the following hardware and software. So, my laptop has an Intel Core i7 processor, and I also have a graphics card from NVIDIA, which is the GeForce GTX 1050, and it has a compute capability of 6.1. Now, uh, the compute capability could be important in terms of installing the following softwares, and you should really look it up before you install anything else. So I installed my GPU driver 445.87 version, and I'm working on a Windows 10 machine, which is 64-bit machine. I installed CUDA 10.1, and for this experiment, it's suggested to use 10.2 plus but if your compute capability is low and if you install a lower version of the driver, then you'll probably have to downgrade to 9.0. And based on the version of CUDA, you also install the cuDNN library. So I've installed 7.6.5, and uh, installation for cuDNN is very simple. It's just a zip file you have to download from NVIDIA's website, and there are three DLL files which need to be copied to the uh, actual location of the CUDA library, the CUDA platform. So it would be somewhere in your program files if you're working on Windows. Then I have used Python for this program, and I would suggest using Python 3. And for the sake of simplifying the process, I've used Anaconda Data Science platform, which means some of my machine learning libraries are already installed. But more importantly, it provides me a seamless experience for building my program in virtual environment. So if you see that I have two different libraries for TensorFlow, one is a normal TensorFlow and the other is TensorFlow GPU. So I can't install both of them together because then I would not know how the program is really working. So I used my Anaconda platform to make two separate virtual environments and installed these two libraries separately in each of them, and that made sure that I keep them separate and I work only on the desired framework at a time. So let's see a demo. So as you can see here, I am activating my CUNN environment right now, where I have installed TensorFlow, not TensorFlow GPU. And I'll start a Jupyter notebook. I already have programmed this model, the CNN model, for me for the sake of this demo, and I've invoked the Jupyter notebook. And as you can see, it shows two files, and I'll start with the MNIST with CPU. And I've already, like I said, I've already written down the program. I've tried and tested it once before recording this video. I've installed TensorFlow, not TensorFlow GPU. I'm repeating it again. And for the sake of this demo, I'll be running all the program cells again. So as you can see, it's asterisk. Okay, so I'm getting the output. So you can see that I've installed TensorFlow Keras here. So I'll be using the Keras library in my TensorFlow. And okay, so here is a bunch of imports and making the model, and I'm just checking how my data looks. And now it's time to train and test the data. So I'll run this again, and look at this. The ETS started at somewhere around 50 seconds, and now it has come down to 25, 24. It's basically quite slow, and there are 5 epochs for this training. So, and this is just the first epoch, and it's taking so much time. And the accuracy started with 60%, but now it's jumping. I think it will jump up to 75 or 76. But my first epoch took 33 seconds. And I have second epoch going on, and the accuracy has suddenly jumped to 91% from 76. Well, I'm already bored, so I'll look at the GPU utilization of my program. There is this command called NVIDIA SMI, which I can use to check GPU utilization. As you can see, it's 0% because, well, I'm using CPU for this operations. And as you can see, each epoch is taking at least 30 seconds, which is a really long time. I mean, I have to wait for another like 1 minute before I get the result. And it's just fourth epoch starting right now. And as you can see, the accuracy is slowly increasing. And we finally have a fifth epoch going on. And it's really, really slow. And I'm training, testing, and I've received a 96.9 and 2.42 minute. Wow. And accuracy of 96.9. Okay. Now I'll go back to quitting this Jupyter notebook, and I'll jump to my other virtual environment, which is GPUNN. As the name suggests, I've installed TensorFlow GPU instead of normal TensorFlow. which means my TensorFlow would be able to access the cuDNN functionalities. And I'll start my Jupyter notebook again. And this time I'll work with the MNIST with GPU program. There isn't much difference in the program. All I've just added 2 lines here to check if TensorFlow works with CUDA. So it's just really checking, and the rest of the program is same. So basically, if I remove the 2 statements that check if CUDA is available, I have the same program, which means you don't really need to change the program. The same program works with CPU and GPU, which is really cool. And I'm rerunning the program like before so as to show you how things work. I'm viewing the data again, checking on the shapes of the training and testing data, and it's time to start training. And as you can see, oh, look at it. Look at the ETA. It's so fast. And I'll check my GPU utilization, and it's 51%. So I'm sure that my GPU is being used for this operation. And look at the times. I mean, first epoch in 10 seconds, second in 6, third in 6, and the accuracy is almost 96 already. And I'm now testing, and I have an accuracy of 96.39 in 35 seconds. It's almost the same accuracy in much, much, much less time. Now, I know that this is something not really significant in this demo because, well, who needs to identify handwritten digits in such a quick time? But I could have done this in some other platform like Google Collaboratory or using a cloud platform like AWS or GCP. But I chose to do it on my laptop because I really wanted to show you how cuDNN, or rather the GPU, can speed up my training and testing operations for deep learning. And this can be really critical for applications like autonomous driving. So the organizations like Uber and Tesla, they use inbuilt uh, they use inbuilt processes. So basically, they don't rely on cloud services when it comes to autonomous driving. I mean, they do have other operations in cloud, but sure, that driving application, the autonomous driving is highly dependent on the local hardware. So each car is installed with a really, really powerful GPU, and all the training and testing is and the running of the model for autonomous driving in real time is done on GPU. And because it's really time critical, you have to make decisions in like a second or so. You can't wait for 2 minutes and 32 seconds for making a decision. By that time, mishaps could have happened. So that's it. This is what I really wanted to discuss here, and I think I've exceeded my time limit. But thanks for listening. If you have any questions, you can reach out to me or you can post your comments in the comment section below. Thank you.